Okay, so in the last class we saw what a multi-layered perceptron is, right? So we saw what a multi-layer perceptron is. So it consists of an input layer. Okay, you have an input layer, multiple hidden layers. Okay, you can have multiple hidden layers and an output layer, right? So that is what we said, output layer. So input layer, the number of neurons depend on the number of features we said, and then the hidden layers. The number of hidden layers is generally one or two, and you can increase it depending on the complexity that or the non-linearity that you want to introduce into the network. Similarly, the output layer also depend on the number of output classes which will be there in the in for the problem. Okay, so this is what we said about the multi-layer perceptron, and we said multi-layer perceptron is a feed-forward network also. Next, what we are going to look at is how will that is once we decide the number of input neurons, the number of hidden layer neurons, the number of hidden layers and the number of neurons in it, and the number of output neurons. Once the design of that part of the network is over, the next thing is we have to decide on the weights. That is, we have to teach the neural network the appropriate weights. And we said that is done using the gradient descent algorithm. So the input to this algorithm, okay, input to this algorithm is we have the network which we said, that is the number of input neurons, number of hidden layers and the number of neurons in it, and the output neurons, and also a random set of values for the weights. We do not know what the weights will be, so we randomly assign a set of weights, and we have a label data set also. That is, in this algorithm input, we are only considering one of the tuples from the label data set, but in sequence we apply every other tuple, and then we keep refining the weights. That is what we do. Okay, so here the input the algorithm only considers one tuple, but we have to go through all the tuples in the label data set, and we might have to go through all the full data set, the label data set multiple times, so multiple epochs in order for the what is known as the network to converge or the error to be reduced. Okay, and for each of the inputs we are giving, we also have the output labels, or the expected output is also given to the algorithm. And in order to the output, of course, is an improved version of the neural network with the weights, uh, weights as well as bias. We are only talking about weights, but bias is also similarly updated along with weights. Okay, so the output is an improved neural network with weights which are closer to or with lesser error. Okay, so what do we do? We first do a propagation, that is, we give the input and we get some output yi as the output to the network, and then from the output we estimate the error using mean squared errors like this, that is your difference between the expected and actual, and then you apply the gradient descent algorithm. Okay, that is what we said. Okay, in gradient descent algorithm what happens is, using the error we have to change the weights. So how do we do that? So what happens is, for each node I in the output layer, so we said there can be I number of neurons in the output layer. Okay, there are I number of neurons in the output layer, and for each of them, for each node j which is input to I, say for example, if you look at this, this is an output neuron, just one layer is shown here, and for each of these, for each input j, okay, sorry, for each input, for each node j input to the that particular layer, now you have to estimate delta wgi. So here, this is our output neuron I, this is the neuron before it in the hidden layer, and what we want to do is we want to correct the weight wji. So you want to find out what is the change in weight which has to be applied. Okay, that is delta WGI. And delta WGI is calculated like this: eta into the di minus yi into yj into 1 minus yi into ya. Now, how do we get this equation? How do we get this equation? We will look at next. Okay, so how do we, that is, we have WGI, we need to change, or you need to bring about a change in this WGI. So how do we estimate that? That is given by our delta WGI. Okay, it can be given as minus eta into dou E by dou WGI. So we said you need uh, a decrease in or a change in the gradient. That is, you need to reduce the error, and that is why we have got this minus here. Eta is the learning rate which we earlier discussed, and dou E by dou WGI, that is the rate of change of error with respect to when there is a change in weight. Okay, that is what we are trying to estimate. So this particular term can be rewritten like this. It is dou E by dou WGI can be written as dou E by dou yi. That is the output here. Yi is the output value into dou yi by dou Si. Now what is Si is? Si is the sum of sigma uh, W Wji into Yj. Wji, that is the output of j here is called Yj, and Yj into Wji is the input which comes here, right? So that summed over all the inputs. Inputs can come from other nodes also. So that is what is the input to this algorithm, right? Input to this node. Okay, so that is Si. Okay, now on that you apply the activation function to get Yi. So that is Si. So dou Yi by dou Si into dou Si by dou Wg. So Si we know is the input which comes here, summed input, and with respect to Wgi, so we can write dou E by dou Wgi like this. Okay. Now we'll estimate each of these terms separately. So what is dou E by dou Yi? It is written here dou E by dou Yi is dou by dou Yi of, so we know E is actually the error, right? So that is what we have written here. We said it is mean squared error, so it is 1 by 2 into sigma m dm minus ym. M is the number of output nodes which are there. So you are summing the error. That is what we write here. Now, so how do we do a derivative of this? Now, what we are saying is we are only considering this particular output node, and if we consider only the y'th term, yi'th term, okay, if you are considering only the yi'th term, okay, here in order to calculate the derivative, say if you look at this, it is a sum of the difference between the expected and actual outputs over all the output nodes. But here we are only considering one of these outputs, yi. So remaining, that is, we are taking a derivative over yi. So remaining y's, that is, apart from yi, other remaining y1, y2, up to yi minus 1 and I plus 1 to m. All those are actually constants when you consider the derivative. So in that case, the remaining, since they are constants, they are reduced to 0, and only yi remains, right? So you need to estimate. So dou dou yi of, so basically it comes to 1 by 2 into di minus yi the whole square. This is what it comes to. So when you take the derivative of this becomes 1 by 2 into 2 into di minus yi into into derivative of this term, which is minus 1, which means you can cancel this out, and this is equal to minus of di minus yi, which is what we get here. Okay, so we have got this term. So we have taken derivative of this term. Next, we look at dou yi by dou si. So dou yi by dou si is equal to dou by dou si of uh, yi. Now yi is what? Yi is you are applying. Yi is the output, right? So to get yi, what you do is on si you apply the activation function. Earlier we saw in the output node, the activation function is a sigmoidal function. So that is why we are replacing yi by this. Okay. Now to take a derivative of this, now how we consider is, you can consider this as something similar to when you take derivative dou by dou x of some u by v. How we take derivative is say v into du by dx minus u into dv by dx divided by e squared. Okay. This is what you do. So how do we calculate that? So u in this case is 1 and v is 1 plus e raised to minus I. So v into, so 1 plus e raised to minus I, 1 plus e raised to minus si into du by dx is derivative of 1 is 0 minus u into, that is 1 into dv by dx is derivative of 1 plus e raised to minus si, which is e raised to minus si by into minus 1 into derivative of this into minus 1 divided by 1 plus e raised to minus si the whole square. Okay, now I'll just rub this. Now this is equal to e raised to minus si divided by 1 plus e raised to minus si the whole squared. Actually, this is the same as what is written here. If we consider 1 minus 1 by 1 plus e raised to minus si, this can be rewritten as 1 plus e raised to minus si minus 1 divided by 1 plus e raised to minus si. Okay. This term can be written like this. So which is e raised to minus si by 1 plus e raised to minus si. That is what is here. E raised to minus si divided by 1 plus e raised to minus si into 1 plus e raised to minus si. So that is here. So it is written like this. So you can say 1 by 1 plus e raised to minus si is yi. Okay. So that is why 1 minus yi into yi. That is what is dou yi by dou si. So this is also derived. Now dou Si by dou Wgi. So how can you calculate that? I'll just rub this off. Okay. Now the third term, okay, dou Si by dou Wgi, which is dou by dou Wgi of, now what is Si? Si we have written as sigma Wgi into yj. Okay, okay, where j varies from say 1 to a number of nodes. J is what is varying. So we said wji is the weight from j to I, where I is the output, right? Now wji into yj is the output from jth node, that is the output comes out of this. Okay, so to this particular node, you will have inputs from all the other nodes in the hidden layer. all the j other nodes. But we are only considering the derivative with respect to wj, this particular weight. അപ്പോൾ അതുകൊണ്ട് എന്താണ്, that is other weights are all considered constant. Okay, but wji where j varies from some 1 to n, only this particular weight is varying with respect to this particular function. Okay, other weights can be considered as constant with respect to wgi. So this derivative can be considered as, ഇത് നമുക്ക് എടുത്തു കളയുന്ന പോലെയാണ്, ബാക്കിയുള്ള വെയ്റ്റ്സിനെ നമ്മൾ കൺസിഡർ ചെയ്യുന്നില്ല, only this is considered. So dou by dou wgi of this will be yg. That is what we get. So now we have calculated derivatives for all these three. So dou wgi can be now written as this. Dou wgi is what we said is minus eta into this term, right? So eta into the first term is dou e by dou yi, which is this. It has a minus, and that this minus actually cancels out. So you have di minus yi into next term is dou yi by dou si. Okay, dou yi by dou si is actually it is this 1 minus yi into yi. So you have got eta, you have got this yi into 1 minus yi, and finally for this term you have got a yg. Okay, this is for this term. Okay, so this is how you derive delta wgi. Okay, so this change in weight is for the layer just before the output. This is for WGI that we have calculated a change in weight. Similarly, for the weight before that, that is for WKI, also we need to come up with some delta value. Okay, so what is the change in WKJ when the error changes? Okay, so that also we write as minus eta into dou E by dou WKJ. Now this term also can be written as this dou E by dou Wkj, that is the change in weight with respect to Ym. Ym is actually Ym stands for the mth output. You can have m number of output nodes, right? So when you consider this node, let me just clear off the. Okay, when we consider, we are trying to find out how Wkj can be changed, right? So, in the earlier case, for this particular case, dou E by dou Yi, we were considering changing Wgi, and the change in Wgi only depend on the error component at Yi. But if you consider this, we know that we have uh, nodes like this, right? You can have I, say, other nodes, that is m number of output nodes are there. So you can have 0 1 2 3 up to n. Say this is some other node, say 3, output node 3, output node 4, and so on. So errors can be there in these nodes also. So these errors also are a factor, or these errors are also propagated back to this wki. But in the case of the original, for this particular layer, the layer which is connected to the output, the weights only depend on the output layer. But before that, the hidden layer weights here, it depends not only on this output, but it depends on all the output nodes. That is why we have a sigma m. That is, we are actually summing the errors over all the output nodes. And that is what m is here. M is the output node. So we write dou E by dou Wkj as the error with respect to the output Ym, and Ym with respect to Sm. Sm we said is the input which comes here, right? The summation which comes here, and it is on this Sm that we apply the activation function to get Yi. Okay, so with Ym by Sm and Sm by Yj. So Sm comes here. Sm is the input here by Ym. Ym alla Yj, sorry, Yj. Sm by Yj and Yj by Sj. Okay. Yj is here, is the output from this node, and Sj is the input to this node. Okay. And Sj divided by dou Wkj. Sj is the input here by dou Wkg. So that is what. So error is actually coming here and error is propagated backwards like this. So that is what this equation shows. The error dou V by dou Wkj can be written as the error which is propagated at each level. Each level you are propagating back, and that is why this algorithm is called backpropagation algorithm. So again, like we did earlier, we have to calculate each of these terms. So dou E by dou Ym. So dou E by dou Ym can be actually, it is similarly calculated like this. Dou E by dou Yi. Okay. Here in this case, it is for only the ith node, but there for all the m nodes we have to calculate. But it is the same formula. So you will get minus dm minus ym. Okay, that is what we get here. Similarly, dou ym by dou sm also we have already computed. Dou ym by dou sm is actually the same value as this. Okay, 1 minus ym by sm, and dou sm by dou yj again, uh, dou sm by dou yj. Okay, dou Sm by dou Yj, if you look at this picture, Sm is the input to this. Okay, rate of change of Sm with respect to Yj, right? And now this Sm is actually a sum of what? Wij into Yj plus etc. for all the nodes. But if you're taking with respect to Yj, all the other nodes are constants. So you only need to consider this term. And dou by dou Yj of Wj into Yj becomes only Wjm need to be here, right? Okay. Similarly, now next is dou Yi by dou Sj. Dou Yj by dou Sj. Dou Yj. Dou Yj is Yj is the output by dou Sj. So that we have to calculate like this, like earlier. Dou Yj by dou Sj is dou by dou Sj of, we said in the hidden node it is the hyperbolic um, what tangent, hyperbolic tangent function. Okay, so you have to apply earlier u by v rule to actually calculate this, and so on.